Alright, in this video here we're going to be talking about linear functions and specifically the slope and the rate of change of a linear function. Alright, so if you didn't watch the video I did on linear functions, a linear function is one that has the form f of x equals ax plus b. Right, a linear function has an x raised to the first power. Right, so the slope of the graph of that linear function is that coefficient of the x. Right, it's that a, that number that's attached to the x. Right, so a is the slope of the graph. Now if you recall the slope formula, it's y2 minus y1 over x2 minus x1. Right? That's how you find the slope of the line that connects any 2 points where the coordinates of the points are x1, y1, and then the second point, the coordinates are x2, y2. Right? So this is the slope formula. Now, the slope formula is also the same thing as the rate of change formula. Right? The b minus a, right? The a and the b are my two x values that I'm talking about, and the f of b minus f of a are those two corresponding y values, right? So the a is like your x1, the b is like your x2, then f of a is your y1 and f of b is your y2, and that's our average rate of change formula. All right, so what all this stuff up here is saying, and if you already watched the video that I did about average rate of change, I already kind of covered this in that video, but the average rate of change of a function is the same thing as the slope of the line that connects those 2 points. And for a linear function, since a linear function always has a constant slope, the average rate of change of that linear function is always just the slope of the line. No matter which 2 points you pick on the line to calculate your average rate of change, it's always going to give you the same value, which is the slope of your line, that number a that's attached to the x. Right now, why we refer to the slope or the average rate of change, why we have these two different ways of referencing the exact same thing, basically what it comes down to is when we're talking about just a pure mathematical problem, like here's a linear function, let's graph that function and find the slope of the line. Well, in that case, we talk about it as far as the slope of the line or the slope of the graph. If we're doing an application problem, though, like a real-life problem or a word problem, where our linear function relates to some real-life situation, generally then we refer not to the slope, but to the average rate of change. Right? If my linear function represents, I don't know, how fast, I think one of the examples we're about to do is how fast we're filling up a pool. You know, there's water pouring into a pool and we want to know the rate at which the water is filling up. Well, we wouldn't say, oh, find the slope of which the water is filling up the pool. That just gets confusing when you use that word slope in a real-life situation. We would say, find the rate at which the water is going into the pool, and that's our average rate of change that we're talking about. So that's why we have these two different aspects of a linear function, the slope and the average rate of change. Right? They're not different. They mean the same thing mathematically. It's just the terminology we use in different situations. Right? We say slope when it's just a pure math problem, not related to any real-life things. Or when we're talking about a real-life situation, we don't really use the word slope. We use average rate of change or just the rate of change, or sometimes just the word rate to talk about that. Right? But anytime you're doing a word problem and you're asked to find the rate, or they tell you what the rate of change is, that's the slope. Right? So they're telling you what the slope of the graph is. So it's an important thing to know that these two different terms mean the same thing. All right, I'm going to pause the recording here and erase these formulas that are up here and put up an example or two where we do word problems that involve linear functions and the rate of change and the slope. All right, got an example here. We have a dam built on a river to make a reservoir. I said that really weird. To make a reservoir. The water level f of t at time t is given by f of t equals 4.5 t plus 28. So let me kind of underline that so it kind of sticks out from all those words in there. Where t is the number of years since the dam was built, and f of t is measured in feet. All right, so a word problem, a basic word problem that we're given. So when you're given a word problem, a couple of things you want to be aware of. Don't just say, oh, there's my equation. Let me just go ahead and start plugging numbers in and see what I get. Make sure you understand what the variables represent and all that stuff. Here, the f of t represents the water level, how deep the water is, which is measured in feet. T represents the number of years, so the time that goes by since we built this dam. So it's important to understand what these things represent so that you can answer the questions correctly and plug the numbers into the right place when that kind of problem comes up. But the first thing we're asked to do here is to graph this function. All right, so if I want to draw the graph, well, first I need to recognize what type of function I have, and this one is a linear function, right? Because I have my t here, my variable is raised to the first power, right? It's in that form, f of x equals ax plus b, right? Even though I have a t here instead of an x, the variable that I use doesn't matter. It's still a linear function. It's still in that form, ax plus b, right? 4.5t plus 28. So I have a linear function, And I know that when I have a linear function, the number attached to the x is going to be the slope of my line, and the b, that constant at the end there, is going to be my y-intercept. All right, so let me draw this graph as best as I can here. So my y-intercept is going to be 28, so let me count by tens here. I'm not going to make a super accurate graph. 10, 20, 30, 40, 50, and let's stop there. And the t's, I won't go too far with the t's. Maybe I will. 1, 2, 3, 4, 5, 6. Let's just stop at 6. All right, and there's 0, of course. All right, so my y-intercept is 28. So if I'm going to graph this, let me go a little bit below the 30 and put a dot there. There's the y-intercept of my graph. All right, now notice I didn't put any negative x values on here. For this particular problem, or negative t values, I should say, in this particular problem, it wouldn't make sense to use like t equals -1 or t equals -2, because t is the number of years since we built the dam, and then the f of t is measuring how deep the water is. Well, for t equals -1, -2, that's 2 years before we built the dam. The reservoir did not exist before we built the dam, so it doesn't make any sense to even look at the graph for negative t values or to think about those at all. Right? So for a lot of word problems, so one of the things to think about is what values actually make sense here. In this case, only from t equals 0 and then positive t values, they're the only ones that really make sense when we're talking about a problem like this. All right, that's not always the case for word problems. Sometimes for word problems, negative values are okay, but not for this one. All right, so we started, when t is equal to 0, our depth of water is 28, right? That's our initial value, that's the y-intercept. And then for each year that goes by, so when t equals 1, I have to add 4.5, right? We have a slope of 4.5, which means I move over 1 and up 4.5, which would give me 32.5. And as you can see, I'm not measuring this very accurately here. I'm just putting a mark a little bit above the 30. And then I move over 1, I go up another 4.5, which would give me something right about there. And then I go over 1 more, up another 4.5. Now, if you need to make this a very accurate graph, I would suggest maybe getting some graph paper and actually measuring, using the squares on the paper to measure and actually, do a good calculation and plot those points accurately so you get a good picture of the graph. But for this purpose, just to kind of see how to graph something and what the graph looks like, this is good enough. All right, so there's my graph of f of t equals 4.5t plus 28. Starting at 0, 28, and then every time I move over 1, I go up 4.5 because that's my slope. Or you can think about it as going up 4.5 and then over 1, up 4.5 over 1, if you're more comfortable doing the rise and then the run. But when we have a linear function, that's how we graph it. Right? Plot the y-intercept or any point really that you have, and then just count the slope. Up this many, over this many, up this many. Or if it's a negative slope, you go down and over, which gives it a downward sloping line. All right, so there's our graph of this function. What is the slope of this line? Well, we already kind of talked about it. The slope is 4.5. Pretty simple, right? When we have a linear function, the number that's attached to the variable is the slope of the line, which we use that slope to draw the graph, so we already kind of knew what that was, right? So my slope is going to be 4.5. Part C, at what rate is the water level changing in our reservoir? All right, at what rate is the water level changing? Well, if you remember what we talked about, 3, 4, 5 minutes ago, the rate of change, and here we see that word. You know what? I spelled the word "what" wrong. One of you guys should have pointed that out to me. At what, I had weight up here with an E on the end. That's weird. At what rate is the water level changing? All right, rate, whenever you see that word rate, you're talking about the slope, right? The rate of change for a linear function is the slope of the line. All right, so when we're asking what rate is the water level changing, well, it's the same as the slope, 4.5, but we give our answer a little bit differently. Right? When I'm asked what the slope is just the number 4.5, and that's it. Slope is just the number. Right? Rate of change is the number, it's the same number as the slope, but we also have to give the units on the answer. So at what rate is the water level changing? It's changing at the rate of 4.5 what? Right? What is changing? Well, what's changing is the depth of the water, which is measured in feet. So it's 4.5 feet per. What time period are we talking about? Well, my t value here is measured in years, right? These numbers here, 1, 2, 3, those represent the years since we built the dam. So 4.5 feet per year is the rate that the water level is changing, right? And the water level is increasing, right? It's getting deeper. The water is going up. That's why there's a positive slope, because the water is getting deeper, right? So it's increasing at the rate of 4.5 feet per year, right? So the slope again, is just the number 4.5. The rate that the water level is changing is not just the number, it's 4.5 feet per year. And when you're talking about a rate of change, there's always really two units there. All right, if you remember the slope formula is y2 minus y1 over x2 minus x1, which I wrote that super sloppy, but hopefully you can read it. All right, y2 minus y1 over x2 minus x1 is the difference in y values over the difference in x values. So when you're doing the units for the rate of change or for the slope, it's the y units or the f units, which are feet, per the x units or the t units in this case, which are years. So it's feet per year. A lot of times students get confused. Well, is it feet per year or is it years per foot? I'm not sure which way to put it. It's always the y per the x, which is like what I said before. You know, when you're doing a word problem, it's important to know what each variable represents, what units are used there, so that when you give your answer, you can give those units appropriately. All right, so the rate of change is 4.5 feet per year. The y units, feet, per the x unit or the t units, years. Always that same thing for a rate of change, y per x, because the formula is the y per or divided by the x. It ties right into that slope formula. All right, so that's one example here of dealing with slope and rate of change of a linear function. I'm going to pause the recording again, put up another example real quick, and we'll talk through that one as well. All right, next example we're going to do here, we have water being pumped into a pool at a rate of 5 gallons per minute. Initially, there are 200 gallons of water in the pool. All right, so the first thing we want to do is write a function to model the depth of the water in the pool. All right, so they give us all the numbers we need here, and you know this is going to be a linear function because the water is being pumped into a pool at a constant rate. Right? If the rate of change is constant, that tells us that it has to be a linear function. Right? So our function is going to have the form f of x equals ax plus b, where the a is our slope or our rate of change, and the b is our y-intercept or our initial amount, right? The starting point. All right, so we just have to read the problem and put the right numbers in the right spot, right? It's being pumped at a rate of 5 gallons per minute, right? So whatever number is attached to that word rate, or another clue for finding the rate or the slope is that per, right, gallons per minute, that's telling you that what you have is the rate of change or the slope, right? So this 5 gallons per minute is going to be my slope, so my f of x is going to equal 5x, and then my plus b, my initial amount, well, initially, there's 200 gallons. So if my initial amount is 200 gallons, that's going to be my y-intercept. So my function that models, you know, the depth of the water in the pool, or not the depth, the amount of water in the pool, the number of gallons that are in the pool, is f of x equals 5x plus 200. Right, where x is equal to the number of minutes that goes by. Right, so x equals the number of minutes, and then the f of x equals the number of gallons of water that are in the pool. Right, so again, when you're writing your own function, it's important to also label what the variables represent. Right, and I know that x is going to be minutes because they gave me here gallons per minute. Whatever time period they give me there, that's what my time, that's the units I'm going to use for the time. If this had said gallons per hour, my x is going to be in hours. Right, if it had said gallons per week, my x is going to be in weeks. All right, and they gave me the gallons here and also gallons here, so my f of x is gallons. All right, so hopefully that makes sense. Again, whatever the rate is your slope, so that's your a, and then the initial amount, that's your y-intercept. Right, when x equals 0, when you first start, you know, filling up the pool, however much is already in there, that's your y-intercept. All right, so that's our function, and then once we write that function, we can use it to answer questions. How long will it take to fill the pool to 600 gallons? Right, so just be careful. I have two choices here. I can put the 600 for the x, or I can put the 600 over here for the f of x. If you put it in the wrong spot, you're obviously going to get the wrong answer. Right? X is the number of minutes that go by. 600 gallons is not an amount of minutes. It's the amount of gallons, which is my f of x, which means I have to put that 600 on the left side of the equation. 600 equals 5x plus 200. Again, read the word problems carefully. Make sure you put that number in the right spot. Important to know what your variables represent, what the units are, so you don't put it in the wrong spot. Right? If f of x is gallons and this is gallons, that 600 goes where the f of x is. Don't plug in 600 gallons for a number of minutes. That's stupid. Right? And then to solve this, I would just subtract the 200 over to this side, which gives me 400 equals 5x, and then divide both sides by 5. And I'm doing this real quick because I'm starting to run out of time here. So 400 divided by 5 would be 80 minutes. All right, so it's going to take 80 minutes to fill up this pool. All right, so once you write your linear function, you can use it to answer all types of questions. Remember, the key thing for linear functions, the slope is the rate of change.